certainly can't move it. Gosh darn it. Stupid thing. Okay, so I can't write over there. All right, final exam, Tuesday, 1 week from today at 4:30, online. And so, I wanted to work through the spring of 20 final. I worked through the fall of 19 final in my other class, and I recorded that. So if you want to go through and look at how the problems are done, I put it on Blackboard. So we'll do the spring of 20 final exam. I still haven't gotten around to making all the keys. I did one of them, I just haven't posted it yet. But I'll do that this week. So problem number 1, we've got two graphs. Y is equal to the square root of 8x and y is equal to x squared. These two graphs enclose a region in the xy plane. So while I write the rest of the problem down, why don't you sketch the graph, find where they intersect, and look at this region. And in part A, we're going to set up the intervals. Just set up only. Intervals to find the area of the region. Volume by rotating about the y-axis using shells. Okay, and volume, about x is 7 using washers. Setting up integrals only. Draw the region. And as a reminder, our plan for using washers is that we make our partitions perpendicular to the axis of revolution. And then it's pi times the outer radius squared minus the inner radius squared times the d whatever. The d whatever is the thickness of the rectangle that we draw. And if we're using shells, our little partitioning element is parallel to the axis of revolution. And our plan is 2 pi RH times the d whatever, which is the thickness again of the partitioning element. But with area, we just partition the region. We'll look at the region, and if it's possible to set it up dx and then dy, we'll do it both ways because that's just what we do. So y is equal to the square root of 8x looks the same as y is equal to the square root of x. You know what that graph looks like? Y is equal to the square root of x as an endpoint at the origin, and it just is a slowly climbing graph. And the other one is the world famous generic parabola. square root of 8x will do something like that. And y is equal to x squared, and pull it up that way. So take a minute and tell me what you find as that far point of intersection. Let's see if I got any juicier markers on here. And I don't. We'll have to make do with what we got. Anybody have the point of intersection yet? The two equations equal to each other. Square root of 8x is equal to x squared. And I guess we'll have to square both sides to get rid of the square root sign. So we have 8x is x to the 4th. Let's move that over and factor. X to the 4th minus 8x is 0. Factor out an x, and we have x cubed minus 8. This gives us the intersection at the origin. And 2 cubed is 8, so x is 2. And when x is 2, I get the square root of 16, which is 4 in either case. So that's the ordered pair 2, 4. So it is a region that's both vertically simple and horizontally simple. So for the additional practice, let's set up the area both as a dx integral and as a dy integral. So dx is top graph minus bottom graph. dy is going to be right graph minus left graph. So take a minute and see if you can do that. Sideways. This is going to be the area problems.
Oh, it's not 2.
It's not 2.
Because the x squared is supposed to be divided by 8.
What x squared is divided by 8?
Like, we did the square root of 8x equals x squared. That x squared is supposed to be divided by 8 because it's 8y equals x squared.
Do I have a what?
Oh, that's an e. Okay, never mind.
Oh,
Over here. It just looks like an e.
sorry.
I was wondering why the area had x squared.
Better?
Okay.
Sorry.
You're good.
Okay, so let's go dx. Top minus bottom dx. So we're putting in a rectangle that goes this way. So the top graph is that square root graph, and the bottom graph is the x squared. So we have areas equal to the integral of the square root of 8x minus, let's say, x squared. That would be dx. And then the integral sign follows the x's. So we're going to go from x is 0 to x is 2. For the dy integral, area is equal to right minus left, dy. And you're going to write everything as a function of y. So y is equal to x squared is going to be x is the square root of y. 8x is equal to y when 8x is y squared, so x is y squared divided by 8. And so when we do right and left, our rectangles look like dy rectangles, and we're hitting the square root graph on the right. So x is the square root of y goes first, and then y squared over 8 goes behind the minus sign. And then the numbers on the integral sign follow the y. So y goes from 0 to 4. Remember all that? Pretty easy stuff. Giveaway points on the final. If I got this one?
Didn't you just want us to set it up?
Yeah, just set it up. Just set it up. All right, so when we're using shells, my plan is up there to take the region and partition it with rectangles parallel to the axis that we're going around. We're going around the y-axis. So here's the picture. Here's our region. We're got the y-axis, so we partition this with rectangles parallel to the y-axis. The length that we're talking about, r, takes us to the middle of that rectangle. That's going to be the r. The height is the height of the rectangle. And since I've got this cut up this way, everything is going to be a dx integral. 2 pi r h dx. So the picture tells you that h is just top graph minus bottom graph. R is the distance between whatever rectangle I place in that little cigar-shaped region and the y-axis. So R is going to vary with which variable? How long is that? Which variable goes this way? X. So the radius is x, height is top graph minus bottom graph, thickness is dx. So that's it. Our volume is the integral of 2 pi r, which was x. Height is top graph minus bottom graph, so just the same as it was here. Square root of 8x minus x squared. And then we follow the x's again from 0 to 2.
When would R be different?
When we move to a different axis. If the axis of revolution is the x-axis or the y-axis, then R is just whichever variable.
So is it always X or Y? Or is it
X or Y. This is
minus
X, and this is Y. Okay, so
only
now we're going to
this
draw the line x is equal to 7, which is something parallel to the y-axis. So R is going to be going in this direction. So let's take a look. I think it's going to be in that direction. Let me draw the picture. There's the x squared graph. There's the square root graph. They intersect at 2, 4. X is 7 is down here a bit. And we're going about that line. We want to do a washer. So remember, we draw things perpendicular. So I'm going this way. And that's cutting up the y-axis. So everything has to be dy. And then we need an outer radius and an inner radius. So the outer radius, start your measurement from the axis of revolution and go back to the farthest graph. That's the outer radius. The inner radius is from the axis of revolution to the inner graph. So it's not quite 7 units. Each radius is shortened from the 7. This one is 7 minus the point on that graph. The inner radius is 7 minus the point on that graph. Okay? So when I put it in my integral, I got my pi right there. Outer radius, again, was 7 minus the point on that graph. That graph is the square root graph. I'm dy though, so I've got to plot my equations again. This one was the square root of y. Oh, sorry, that one was what? Yeah, that one was the square root of y. And this one was y squared over 8. So do you agree that the outer radius is 7 minus y squared over 8? Outer radius squared minus the inner radius squared. So that's going to be 7 minus that point, which is the square root of y. And then we follow the y values, which go from 0 to 4. So let's do a couple of what ifs. If we take that same region, what if we take that same region, revolve about x is -1, and use washers? What changes? Already I will change. Here's the picture again. Here's x is -1. There's, we're going to use washers. We go perpendicular. So the outer radius has gotten longer. And there's the inner radius. Still dy. Can somebody tell me what the outer radius is going to be? Square root of y plus 1. Here to here is the square root of y, but then I'm going one further. Outer radius squared minus inner radius squared. So we take this graph that's on the left and add that 1 unit to it. So I take y squared over 8 plus 1 squared dy. And we're going 0 to 4 as well. Okay? You happy with that problem? Need another what if, or are you good with that? Okay? Okay, I'll rub it out. We'll do the next one. Okay, a cylindrical tank, so it's shaped like a can, has a radius of 4 feet and a height of 10 feet. Draw a can, radius 4 feet, height of 10 feet. It's filled with a liquid, and we're going to pump the liquid to the top of the tank. The liquid weighs 70 pounds per cubic feet. Full tank with that amount of liquid, the tank has a radius of 4 feet and a height of 10 feet. We want to find the work done in pumping out the liquid to the top. So if I'm in pounds per cubic feet, pounds and feet here, what are the units on work? In this example, and I've got pounds and feet here. Foot pounds, right? We want our answer to be in foot pounds. So we need to compute a force in pounds and a distance in feet. The product of force times distance gives us work. So in order to get our force in pounds, we need to begin with something here. We've got pounds per cubic feet. So we're going to multiply that by cubic feet to get rid of the cubic feet, and that'll give us our force in pounds. Cubic feet is a volume measurement. It's not the volume of the tank, it's the volume of the slice of water or liquid that we move to the top of the tank. So here's the slice of liquid. We've got to find its volume. The shape of the tank determines how we compute the volume. Since our tank is a cylinder, the volume is a fixed disc like that going all the way up. So for the force, we start with our density times the volume of the slice. And since our slice is a disk, we've got a little pi r squared times its thickness. I do things up and down the y-axis, so my thickness is going to be a delta y. So the volume of our slice is pi r squared times delta y. If you have a cylinder, the radius doesn't change. It stays the same as the radius of the can. When we had a cone or some sort of parabolic shape, then we had to use the equation that generated the radius because it changed as we went up. But this one, the radius stays the same all the way up, stays the same as the radius of the container. So this is just going to be pi times 4 squared times our delta y, which is going to become the dy on the integral. So that's the volume of the slice in cubic feet. And then when you multiply those two together, there's our force in pounds. Now the distance is how far that slice has to move in feet. We're pumping it to the top. So if this is on the y-axis here, this is the ordered pair 0, 10, and I placed it at some arbitrary y coordinate. So what are you going to use as your distance? 10 minus y. And now we put that in an integral sign so that we can sum up all of those slices, and we get a work integral of the 73 pi times 4 squared times my dy, and then the 10 minus y here. And then the depth of the liquid reflects the numbers on the integral sign. This container is full, so we're going to integrate from 0 to 10. If it's filled to a certain level, we integrate 0 to that level. Okay. So here it's full. Good. The other type of problem would be, for instance, if you turn this tank on its side so that you have a circular face facing you, and now that fluid puts a force acting on that circular face. Force on a horizontal plate is constant. The force on a vertical plate is variable. And force is not dependent on the shape of the container. It's a two-dimensional quality. It's acting just on a single face. Force is going to be in units of pounds. So we've got to take this thing here and get rid of the cubic feet. But since we're in two dimensions, we take a slice of the plate, which will be some sort of rectangular strip, and we find the area of that strip, that'll be square feet. So it's the length, right graph minus left graph, times the dy, there's our area. Length times dy, and then the depth in feet. And the depth is the same as before, surface of the liquid minus y. Okay? So the only thing that's missing is this volume thing. We got length, dy, and then distance to take care of the cubic feet. Okay, number 3, I'm going to put 4 integrals up here on the board and see if you know how to do these 4 integrals. Go ahead and write the first one down so you can get it started. We've got a fraction that has 3x minus 1 on top. And on the bottom, I believe we've got an x plus 5 times an x plus 1. You can do that integral while I get the other 2 written down here. C didn't take any room at all. That's why I just left a little bit of room there. You see your 4 favorite integrals up there, right? And the order that we covered them in section 1 was a review of all of our substitution integrals. Section 2 was integration by parts. Section 3 were those trig integrals and trig subintegrals. section 4 were partial fractions. Then we reviewed them again in section 5. So we've got one of each type in those 4 sections. So this one, of course, is partial fractions. Keep working. I'm just going to put my answer up here and you can compare. Did you get A as 4 and B as 1, or get 4 and 1 as the numerators? So I got A to be 4, that's the numerator of the x plus 5. And then negative 1 be the numerator of the x plus 1. And since those are just first degree factors in x, they're 1 over u integrals, they're both logarithms. So our final answer is 4 times the natural log of the absolute value of x plus 5 minus the natural log of the absolute value of x plus 1. So let me ask the what if cases. What if you had the same problem, but maybe the x plus 5 was squared? How do you start? What's the difference between that one and that one? That's right, and the numerators are still constants. You're going to have the a over x plus 5, but then you're going to have something over x plus 5 squared. It's still going to be a constant. And then when you're doing this integral, you're integrating u to the negative 2 du, and it's not a logarithm, right? That'll give you a minus u to the minus 1. The other what if case, what if I had that as x squared plus 5 times x plus 1, with the square on the inside? How does that differ? That's right. You have above the x squared plus 5, you have to put a linear factor. This is still this one you probably have to break up into two integrals. You'll have whatever a times x is over x squared plus 5, and that's a u du integral. What about a constant over x squared plus 5? What's the value of that integral? Just a constant over x squared plus 5. Remember, forgot that one? Suppose I just put a 1 up there. What is that integral? Won't be a natural log. You get a natural log when you have the x to the first power. That one's going to be a natural log. That'll be a 1 over u du, but not this one. That's an arctangent. In this case, it'll be the arctangent of x divided by the square root of 5 with a 1 over square root of 5 here. So this one is going to be the arctangent. The other one's going to be a logarithm. So it probably wouldn't hurt you to look at one of those all the way through. All right, take your time and do the second one carefully. What technique are you using on the second one? Integration by parts. Do you know how many times you have to do it? 2 times. Because the x is squared, so if you want, you can do this in table form. Do an integration by parts by table. The x squared has to be the u term. The dv term has to be the sine of 3x. What do you get when you integrate a sine of 3x? And it's a negative 1/3 cosine of 3x. The 1/3 comes from the angle inside. Each time you integrate sine or cosine of 3x, you get a 1/3 out front. Angle of sine is a minus cosine, angle of cosine is positive sine. Remember integration by parts formula. The integral of u dv gives you uv minus the integral of v du. Gives you a table form. You don't have to worry about that. You just go down the diagonals. Which way are you doing it? Table form or with the formula? Table. Okay, so in the table form, you pick a u and a dv. U is x squared. We keep making rows until I run out of derivatives. I need one more. dv is the sine of 3x, and we start integrating. Remember, negative 1/3 cosine of 3x. And then another 1/3 gives me a negative 1/9 sine of 3x. One more time, I get a negative of a negative is a positive, 1/27 cosine of 3x. Then we go down the diagonal, plus minus, plus minus. That one's plus, that one's minus, that one's plus. So our first term is a negative x squared over 3 cosine of 3x. Then we have a minus 2x times a minus 1/9 to give us a plus 2x over 9 sine of 3x. And our last term is a plus 2 times 1/27, so 2/27 times the cosine of 3x, plus the constant of integration. Any questions? Okay. So why did I say part C was so short? It's u du integral. And anytime there's a logarithm as part of the integral, that's u. So you take u to be the natural log of x. Our integral becomes the sine of u. The stuff that's left is the 1/x dx, and that's the du term. You can see it right off the bat, then it's quick. U is the natural log of x. Du is 1/x dx. And this is simply the integral of the sine of u du. So it's minus the cosine of u, but u is the natural log of x. I'm going to move the other one down here. That's not a u du integral because I have an x squared under the radical sign and no x to the first outside of the radical sign. So in doing that one, we're motivated by our Pythagorean identities. From this one, we have sine squared of x plus cosine squared of x. I guess I better use theta so that you don't use x's when you substitute. And so if I solve that for cosine squared, there's one version. Then we had tan squared of theta plus 1 is secant squared of theta. And then we had secant squared of theta minus 1 is tan squared of theta. So for this one, we use a sign if the variable squared is behind the minus sign. If the variable squared is in front of the minus sign, we use a secant substitution. And if things are added, we use a tangent substitution. We have the variable squared behind the minus sign. So that's your hint that you're going to let x be some version of a sine of theta. So let's see if you can make that substitution. Don't forget the dx term. And see if you get an integral that you know how to handle after that. once you get rid of the radical sign, you're integrating the cosine squared of something? Is that what you're getting? The cosine squared to integrate. Anybody there? So to help get rid of the 9, you're going to take x to be 3 times the sine of theta, so that when you square it, you'll get a 9 sine squared. Also need a dx term, and that'll be 3 times the cosine of theta. Let's put those in. That'll be 9 minus 9 sine squared of theta times 3 cosine theta d theta. You can factor out the 9 and have a 1 minus sine squared under the radical. And then 1 minus sine squared can be replaced by cosine squared. So that's what's under the radical. And it's a product, so now you can take the square root of each term in the product. And so you're going to get a 3 cosine theta multiplied with another 3 cosine theta. And so we're integrating 9 times the cosine squared of theta. That one's a formula. What's the integral of cosine squared? 8 over 2. Cosine has a plus. Sine of 2 theta over 4. And then we get the theta from here. X over 3 is the sine of theta. So theta itself is the inverse sine of x over 3. If I write the sine of 2 theta as 2 sine theta cosine theta, I can put a substitution in there. This one we said was going to be the inverse sine of x over 3. I'm going to replace sine of 2 theta with 2 sine theta cosine theta. Cancel a 2 with a 4. Sine of theta is x over 3. Let's draw a picture and figure out the cosine of theta. That should be the third side there. Cosine is adjacent over hypotenuse. So this will be 9 minus x squared over 3. So we had that handy dandy identity. Help us write the double angle in terms of the single angle. Makes our answer look prettier. We're all about being pretty answers. Question, John?
If we were to just leave sine 2 theta, we just put in theta.
Yeah, you can put your inverse sine of x over 3 there. I just like to make it look prettier. Okay, so that one we would use for this form. We do a secant substitution. If it were the other way, we do a tangent substitution if there's a plus. Okay? A secant substitution in the variables in front, a tangent substitution when it's plus, a sine substitution when the variable's behind the minus sign. Okay? And then in that section, we had some integrals. Remember the formulas for the integral of sine squared, cosine squared? What's the integral of a tangent? That's a derivative tangent. What's the integral of a tangent? Let's spot you a natural log. You didn't forgot that one? We can always write the sine over cosine and do a u du substitution. Remember that one? What about the integral of a secant? Another natural log deal. Secant plus tangent. Secant theta plus tangent theta. And then the bonus round, integral of the cosecant of theta. Got you that part. It looks like his cousin. Cosecant plus cotangent. Okay, so those are a couple things to put back into your memory. There we go. Still can't see him. Shouldn't have written down there. I'm not going to move that camera again. It'll shut off. And look up the integral of tangent, integral secant, integral cosecant. Okay, now we're getting to the sequence and series part of the course. So, let's look at this. What does it mean for a sequence to converge? Sequence converges if it has any limit. Sequence converges if it has any limit. Series converges by one of our tests. Okay? Sequence converges if it has any kind of limit whatsoever. Series converges if it passes one of our series convergence tests. And so for this next problem here, you're given you're asked if the sequence 3 to the k over 5 to the k converges, if so, to what? And the same thing with that as part of a series. Converge or diverge, if so, to what? Say it again? This was on the final from whatever, fall of 20. Yeah, sure.
The last one.
This was on our last exam. For this one, you're just checking the limit. K goes to infinity. 3 to the k over 5 to the k. Got any feeling about that one? 0 because bottom heavy. So it converges to 0 because it has a bigger bottom. Okay. If that limit were not 0, then we wouldn't have to do part B. If that limit were not 0, then part B would be a divergent series. Because a necessary condition for convergence of a series is the general term go to 0. But a sufficient term for the convergence of a series is something totally different. We've got to figure out why that series converges now.
What's the start at?
It doesn't matter. We can start at 0 if you want. I guess that we have to know so that we know what it converges to. So what kind of series do you have looking at you there? That is a geometric series. And if you write out the first few terms, anything to the 0 is 1. The next term is 3/5. The next term is 3 squared over 5 squared, and so on. So R is what? 3/5. Is that a size that tells us that it converges or diverges? Converges because R is smaller than 1. And we always look at R in absolute value. And then we have a formula to tell us what it converged to. What's the formula? A over 1 minus R. A is the first term, so if K start at 0, it's 1, and R is 3/5. So I get 2/5 on the bottom, 1 over 2/5 is 5/2. This thing converges to 5/2. Next one. I'm going to put 4 series up here. Thank you. And the question is converge or diverge? Why? So while I'm writing them down, think of your favorite series test. See if you can list all the series tests that you know. Can't walk that far. So some of the first tests that we learned were the obvious ones. The one we just used was a geometric series, but you should also be able to recognize P series and Q logs. There's always a test for divergence somewhere on the final. So I'm going to get you to look for that first. Look at these 4 problems and see See if any of them diverges by the test for divergence. D. 2 to the k grows faster than k. Look for that first. Look for your test for divergence problem. Yes, sir.
How much work would you want to show in that divergence problem? Can you show that?
If you just tell me this, say that limit as k goes to infinity of 2 to the k divided by k is infinity, so it diverges by the test for divergence. All right, you can even say that that's not 0. All right, 2 lines. 2 lines is all you need to put for that. So that's the only one that diverges by the test for divergence. I'll let you play around with the other ones for a few seconds. They're all very short. Anything obvious to do on 4A? Ratio test. K power and K factorial. Do a ratio test on this one. In the ratio test, we look at a limit. How big does that limit have to be? Or what size does it have to be for it to converge? Less than 1 converges, bigger than 1 diverges. Equal 1, try something else. And the limit is k plus 1 term divided by the k term. So the k, 4 to the k's will cancel, leave me a 4 to the first power on top. K factorial cancels, leaves me k plus 1 on the bottom. So you get a limit of 0, so it converges. Bonus time, what does this one converge to? Nope. Whose power series looks like x to the k over k factorial? E. X to the k over k factorial is e to the x. So 4 to the k over k factorial converged is e to the 4th. Right? If they look like one of our favorite McLaurin series, we can tell what it converges to. Did you get a chance to try B? What do you typically try when you have polynomial divided by polynomial? Comparison test. So we're going to compare to, we just throw away the numbers. And we make a series out of that and simplify it, just becomes 1 over k. So tell me what you know about our comparison series. It's going to diverge. So in the direct comparison test, bigger than divergent is divergent. In the limit comparison test, any limit says both series do the same. So do you want to mess with the work of seeing if that's bigger than divergent, or do you just want to go straight to the limit comparison? Limit comparison is quick and painless. We look at the limit of the given series. With the one that we built. That'll give me a k cubed on top and a k cubed on the bottom. So my limit is 1. Any positive finite limit means both do the same. And that means this given series diverges. Probably the quickest way to do part C is to make the sum of two series here. Because I recognize 2 over k as being my divergent P series. What about the log of k over k? It's a divergent Q log series. And divergent plus divergent is divergent. That's only for plus, right? We've seen some of our telescoping series with a minus sign here. Minus is not the same. Divergent minus divergent is not necessarily divergent. Those are typically telescoping. But plus divergent plus divergent, divergent plus convergent are both divergent. Convergent, if I had a k cubed down here, I can say the same thing with convergent. Convergent plus convergent is convergent. But one bad divergent in there and you're divergent. Minus is everything out the window. Okay, only for plus.
What if you had convergent plus divergent?
Once you put a divergent in there, it's divergent. Right? Convergent plus divergent is divergent. Divergent plus divergent is divergent.
About convergent plus convergent.
Convergent plus convergent is convergent. Right? It's like your mama always told you. One bad apple spoils the whole bunch. Right? You stick with the good apples. Convergent plus convergent is convergent. Okay, what's a Maclaurin series? Maclaurin series is centered around 0. Give me the first 3 terms of the Maclaurin series for the natural log of x plus 3. First 3 terms of the natural log of x plus 3. This is problem number 6.
What was number 5?
That was number 5? Yeah, that was number 5. Number 4 was the geometric series. So sorry, I can't count. That's 5. So the center is at x equal to 0. So our series is going to be f of 0 plus f prime at 0 times x over 1 factorial plus f double prime at 0 times x squared over 2 factorial. That's the 3 terms we're looking for. So knowing the formula gives you most of it. there's your first three terms at x. Natural log of x plus 3 has as its derivative 1 over x plus 3. The derivative of 1 over x plus 3 is negative 1 over x plus 3 squared. So when we evaluate those at 0, I get the natural log of 3 as my lead term. F prime at 0 is 1/3. F double prime at 0 is a negative 1 over 3 squared, or a negative 1/9. And so this looks like the natural log of 3 plus 1/3 of x divided by 1 factorial, which is just 1, minus 1 over 9, 1 over 9, x squared over 2 factorial. Okay? All right, the last problem here is problem number 7. Problem number 7 has our vectors. Probably fit it right there. Let's see, we got a vector u whose components are 2, 0, 3. A vector v has as its components negative 1, 1, 0. You are asked to find the magnitude of u. You are asked to find u minus 2v. And let's just add a couple more. Let's find u dot v. And then, of course, u cross v. So you can find those 4 things in 5 minutes or less. All right, I'm going to go ahead and work them so that you have the answers. Magnitude of u, we square each component, add them together, stick it under square root sign. 4 plus 9 is 13. Magnitude of u is square root of 13. U minus 2v will be 2, 0, 3, minus, now I'm going to double the components of v, negative 2, 2, 0. Then we subtract component-wise. 2 minus a negative 2 is 4. 0 minus 2 is a negative 2. 3 minus 0 is 3. So 4, negative 2, 3 is the difference. Square root of 3 is the magnitude of vector u. Is the dot product between two vectors a vector or a scalar? Scalar. So u dot v, we do the numbers. X times x is a negative 2 plus 0 times 1 is 0 plus 3 times 0 is 0. U cross v, v is the vector that we get when we do this 3 by 3 determinant. So we get an I component. And remember that we have a minus sign in front of the J 2 by 2, and then the K 2 by 2. To get the I one, we cover up the I column, so we have 0, 3, 1, 0. To get the J, we cover up the J, 2, 3, negative 1, 0, and then 2, 0, negative 1, 1. So this is going to be 0 minus 3I. This is going to be 0 minus a negative 3J. And this is going to be 2 minus 0K. So minus 3I minus 3J plus 2K. And how do we check our answer on the cross product? If the dot product with any of our two vectors here is 0. So I'm going to dot it with this one. That's a positive 3. That's a negative 3. That's 0. This dot that is 0. That means those two vectors are perpendicular. How can you tell if two vectors are parallel?
The cross product, the factors of one another in a way.
One's a factor of the other, right? Something parallel to this would be negative 3, 3, 0. Okay? All right, so you need to look at some of the other tests and look at some of the other formulas. Some of the things that we did that were not reflected on this test was area and our basic graphs and polar coordinates. Going through the chat, the arc length in rectangular and polar coordinates, make sure you look at those formulas. Again, look at the force in the applications in chapter 6. And I think you did a representative of every integral. Good? Okay. It's been fun. So have you guys loose? I'll see you zoom in on me on Tuesday. And then when you guys are taking Cal 3 or linear algebra, come by and see me and show me what you can do. I can help you with your homework, you engineering kind of people. Yeah.